All right, welcome. We're going to do discussion 9.2, electrochemistry. This is the final discussion in the core material. And so after this one, we'll be able to review everything we've done this year before we dive into our option. All right, so in this unit, we're going to look at electrochemical cells. And there's two types of cells we're going to look at, voltaic cells and electrolytic cells. A voltaic cell is a device that converts chemical energy into electrical energy via spontaneous reaction. This is essentially a battery. An electrolytic cell is a device that uses electricity to force a non-spontaneous reaction to occur, creating chemical energy. So in both of these cells, redox reactions are occurring, and if you look at the definitions, you will see that these two types of cells are opposite of each other. So for some definitions, electrode is the site of oxidation and reduction in an electrochemical cell. The anode is the electrode where oxidation occurs, and the cathode is the electrode where reduction occurs. An easy way to remember this is by saying red cat and ox. Reduction, occurs at the cathode, and oxidation occurs at the anode. Now it's important to note that even though the two types of cells are opposite from each other, this will always hold true. Reduction always occurs at the cathode, and oxidation always occurs at the anode. It does not matter which type of cell it is. So voltaic cells. A more thorough definition, in a spontaneously occurring redox reaction, electrons will be transferred. Now we can separate those half reactions into two different vessels and force the electron transfer to occur through a wire. Then we can harness it. And this is actually how batteries work. Batteries are voltaic cells. So let's go ahead and diagram a voltaic cell for you. Okay, so a voltaic cell, will consist of two separate vessels. Often we'll use beakers. The cell on the left we'll call the anode, and this will be the negative electrode. The one on the right we'll call the cathode, and that is the positive electrode. Now, the anode is almost always written on the left, so get in the habit of doing that. In both vessels, we will have a solid electrode, and those electrodes will be attached to a wire and connected to a voltmeter. Each electrode will be immersed in an electrolyte. Now remember, oxidation always occurs at the anode and reduction always occurs at the cathode. So what we're going to do here is look at the reaction between zinc and copper 2 sulfate. And in this reaction, we're going to be producing copper and zinc sulfate. Now if I look at all the oxidation states of all the elements in this reaction, I see that zinc going from 0 to +2 is oxidized. That means that the electrode at the anode will be made out of zinc. And copper is reduced, so copper will be the electrode at the cathode. Now, both cells will be connected with a device called a salt bridge, and we will talk about the function of the salt bridge in a couple of minutes. So oxidation is occurring at the anode. So zinc at the anode is being oxidized into zinc ions. So the electrolyte at the anode will be a solution of zinc sulfate. Right, now, once the zinc is oxidized, electrons will be removed from the zinc. Now, those electrons are going to be attracted to the positive electrode, so they will travel from the anode to the cathode. Now, at the cathode, reduction will occur. So copper ions are going to be reduced into solid copper. So the electrolyte at the cathode will be a solution of copper 2 sulfate. Okay, so the equations for what we're seeing here, we can see up here. Now, if we broke this into the half reactions, we would see that zinc is being oxidized to zinc 2 and freeing up 2 electrons for every atom of zinc. And copper is being reduced into, copper 2, is being reduced into copper by accepting those electrons that are coming from zinc. All right. So the salt bridge. The purpose of the salt bridge is for ion migration. And the salt bridge will usually be filled with some kind of salt that will not interfere with what is occurring in the cells. Often it's potassium chloride, so I'll write potassium and chloride ions. Now as the electrons leave the anode and travel to the cathode, the anode will become more positive. So the negatively charged ions in the salt bridge will migrate into the cell, equalizing the charge and keeping the charge from getting too spread out over the two cells. Now, as the electrons travel to the cathode becomes more negative, so positive ions will migrate into the solution from the salt bridge. And let's see if there's anything else I want to say here. Oh yeah, so you will see over time the mass of the anode reduce because the zinc that's in that electrode is being converted into zinc ions in the solution. And conversely, the mass of the cathode will increase because the copper ions in solution are being reduced into solid copper. So the important things to be able to label are the cells themselves, the anode as negative and the cathode as positive. You want to show the ions that are present in solution, the identity and charge of the electrodes, the salt bridge, and the direction of electron flow. And if you're asked to produce equations, then you can just produce the half equations that you see in the overall reaction. All right. So it's important to note that the more reactive metal will always be at the anode, right? Because the more reactive metal will always be oxidized, as we will see. And the electrons always flow from anode to cathode. All right, so back to the PowerPoint. All right, so how can we determine if a reaction will be spontaneous or not? All right, so here I have copper attempting to react with aluminum chloride and aluminum attempting to react with copper 2 chloride. Now, copper, when it reacts with aluminum chloride, you'll see nothing happen because aluminum is more reactive than copper. Right? Aluminum, because it's more reactive, will be oxidized over copper, and so copper cannot replace it as an ion. So if aluminum reacts with copper 2 chloride, you will indeed see a reaction, and you'll see copper and aluminum chloride produced because aluminum is more reactive than copper. So another way to tell which metal will be more reactive is by looking at what is known as an activity series. Now, the activity series is a spectrum of the elements, vertical, raised from the most active to the least active. What that means is the elements higher in the series are more reactive than ones that are lower in the series. And we can see that aluminum is above copper in the activity series. So if we had to determine which of those reactions occur, we would need to look at the activity series. Now, the elements at the top are more reactive because they have a higher potential to be oxidized than elements below them. That makes them good reducing agents. And the elements at the bottom will have a higher potential to be reduced or a lower potential to be oxidized, so they are better oxidizing agents. All right, so let's do a little practice with an activity series. It says consider the following 3 redox reactions. Now it wants us to deduce the order of reactivity. So basically it wants us to create an activity series. So if we look at the first reaction, we see that cadmium is reacting with nickel 2 ions. And the cadmium is replacing the nickel 2 ions to produce solid nickel and cadmium 2 ions. So we can say that cadmium is more reactive than nickel. In the second equation, nickel is replacing silver, so we can say that nickel is more reactive than silver. And in the final equation, we see that zinc is replacing cadmium 2, so zinc must be more reactive than cadmium. So it wants us to list these in order of decreasing reactivity, so that means most reactive to least reactive. If I look at the data I have here, I see that zinc is more reactive than cadmium, and cadmium is more reactive than nickel, and nickel is more reactive than silver. That means that our order of reactivity must be zinc is the most reactive, followed by cadmium, then nickel, and finally silver. So if we want to identify the best oxidizing and best reducing agents, we have to consider what the activity series means. Zinc would be at the top of our activity series, so that means it is the best reducing agent. And because silver is at the bottom, it is the best oxidizing agent. All right, so line notation. This is just a simplified way of showing the reactions that are taking place in the voltaic cell. So we do line notation by first showing the oxidation process, and we separate the products and reactants of that process with a single vertical line. We'll then put a double vertical line separating the two cells. Then we'll do the same thing we did for reduction, or for oxidation, for reduction. So for the reaction we did in our voltaic cell, this is what it would look like. In that cell, we had zinc metal being oxidized into zinc ions. And in the next cell, which we'll use a double line to separate, we had copper 2 ions being reduced into copper. When you first see line notation, it might look a little confusing, but you'll get used to it fairly quickly. All right, so now let's look at the electrolytic cell. In an electrolytic cell, is used to force a non-spontaneous reaction to occur. So in this reaction, we're converting electrical energy into chemical energy. So I want to just diagram for you a general electrolytic cell. So the voltaic cell consisted of one electrode. So the electrolytic cell will consist of, or one vessel. The electrolytic cell will consist of one. That one vessel will have the electrodes in it, and those electrodes will be connected to a battery. And we know a battery has a negative pole and a positive pole. The electrodes will also be immersed in a solution, in an electrolytic solution, an electrolyte, excuse me. So that solution will consist of cations, which we'll call X+, and anions, which we'll call Y-. All right, so once we connect the battery, the electrons will flow from the negative pole into this electrode, creating a negative charge on it. Right? That will put a positive charge on the other electrode. Now, in a battery, the negative pole is negative because all the electrons reside on that side of the battery. So they want desperately to get to the other side, but they're blocked by a barrier. So the only way for them to travel is through an external circuit, through this electrode, through the electrolyte, little dotted line showing the electrons, back to the positive pole. Now, once you create a negative charge on that electrode, it will attract the positive ions. And the positive ions will accept the electrons that are being freed up there, and they will be reduced. So reduction is occurring at this electrode, and since reduction is occurring there, we will call it the cathode. And the reaction occurring there would show those X+ ions being reduced into solid X, or whatever state that element happens to be in. Now, because this electrode is positive, it will attract the anions, and the anions will be oxidized. So since oxidation occurs there, we will call this the anode, because red cat, anox. So there, the anions are being converted into metal and freeing up an electron as they do so. Not metal, elemental, excuse me. All right, so the important things to label in the electrolytic cell are the cell itself, the electrodes, the battery with the poles connected to the proper electrodes, and it's easy to remember that the positive electrode is attached to the positive and the negative electrode is attached to the negative. You'll want to show whatever ions are present in the electrolyte, be able to produce the equations at the anode and the cathode, and be able to label the anode and the cathode. Okay, so here just summing up the two cells. In both voltaic and electrolytic cell, we have red cat, anox, so oxidation occurs at the anode, and reduction occurs at the cathode in both of them. But in the voltaic cell, the anode is negative, just like anion, and the positive electrode is the cathode, just like cation. Now, that is what is reversed in the electrolytic cell. In the electrolytic cell, the anode is the positive electrode and the cathode is the negative electrode. All right, so uses of electrolytic cells. There's three main ones. We're only going to look at two of them here. They're used for rechargeable batteries, for the isolation of pure elements from compounds, and electroplating. And we are specifically going to look at the second two. All right, so let's look at what happens during electroplating. So electroplating uses an electrolytic cell. So let's go ahead and draw our single vessel with an electrode, an electrolyte, and the object we want to be plated. So let's just assume this is a silver coin, and there's my president face on it. All right, so both electrodes will be attached to a battery. And we have to determine which will be the positive and the negative charge. So if I wanted to plate copper onto this coin, I would need a solid copper electrode, and the electrolyte would need to contain copper ions and usually sulfate ions, because sulfate ions will not participate in oxidation and reduction. So if we want to plate copper onto that coin, we have to make that coin attractive to the positively charged copper 2 ions. So we'll make the coin the negative pole and the copper electrode the positive pole. Right? So because the coin is the negative cell, or the negative electrode, that means the copper ions will be reduced there into copper metal. Right? So we can say that this is the equation occurring at the cathode. And at the anode, copper ions are being oxidized to produce more copper 2. So at the anode, we will have copper turning into copper 2 and freeing up 2 electrons. Right? So as the copper ions are reduced, they will be formed onto the coin as elemental copper, and so we'll form a thin layer of copper over that coin. All right, so there's a number of different factors that can affect the amount of metal plated. One of them is the amount of current supplied by the power source. So current is the rate of flow of electricity. So the greater the current, the faster the flow of electrons, and so the faster oxidation and reduction will occur, and the more metal you'll get plated. Also, the charge of the ions being reduced. If we looked at copper 1 versus copper 2, a mole of copper 1 would need to accept 1 mole of electrons per mole of ions, and copper 2 would need to accept 2 moles of electrons for every 1 mole of copper ions. So copper 1 would be plated faster than copper 2. And finally, the concentration of the solution. The more concentrated the solution, the more ions you have in it. So the faster electricity will be able to flow through it, and the more ions will be available for reduction. Now, there's other there's other factors at play here, including the temperature of the solution and or the surface area of the electrode, but these are really the big 3. All right, so now let's look at the electrolysis of a molten salt. So now, when I say a molten salt, I mean a salt that is melted. So what we have here is molten sodium chloride. So in our electrolyte, we're going to have liquid sodium ions and liquid chloride ions. We have our negative and our positive pole. So once we connect the battery, the sodium ions will be attracted to the negative pole, where they will be reduced. So the reaction occurring at the cathode will be sodium ions being reduced into solid sodium metal. Okay? And at the anode, the chloride ions will be attracted by that positive charge, and so they will be oxidized into elemental chlorine and form electrons. So we have to be sure we balance this half equation to show this. Now, a thing I want to ask you is which of these will be produced at a faster rate, sodium or chlorine? So pause the video for a second and try to work that out. Okay, so sodium ions need 1 electron to be reduced, and the chloride ions need 2 electrons to be oxidized. So sodium will be produced at twice the rate of chlorine. Now it's important to note, this is a common mistake, whenever we're writing the equations for these processes, that the first step will always be the ions, because before we connect that battery, what you've got here is your electrolyte, which consists of liquid sodium ions and liquid chloride ions, right? So the first step will always be the ions. All right, so here I want you to practice a little bit by deducing the reactions that occur at the anode and the cathode for the electrolysis of molten silver iodide. Okay, so actually there's one more thing I want to show you guys over here. Now, usually when we do this process, the electrodes will be made out of graphite. Right? We don't want any more ions being produced by this process. We only want the sodium and chloride ions in there, and graphite electrodes are exceptionally conductive, so they are generally used for this process. Okay, moving right along. So to deduce the reactions that are occurring at the anode and the cathode for molten silver iodide, we want to first consider what's going on here. Now we know that we're going to have silver ions and iodide ions. Right? And that's going to be the starting point. So what you're going to want to do is just start with the ion and draw an arrow going from it. Right? Now we know that in both processes, we're going to form the elemental forms of these elements. Right? So when we balance these equations, we see that we have to add an electron to silver in order to reduce it. Since it's being reduced, this is the equation occurring at the cathode. Now for iodine, we see that iodine will be oxidized, anox, so this is what's occurring at the anode. Now once you get used to this, you don't actually have to draw the cell to produce the equations. Just remember that we're always going to start with the ions and finish with the elements. All right, well, I believe that is it. Yes, it is. Final video lesson for the core material. This requires some practice. If you have any questions, please bring them to class. And as always, thank you for watching.